Please like, share and subscribe our channel to learn and enjoy our free online educational videos from class nursery to 10. Please click the bell icon to get all new updated videos. Lesson 4. Carbon and its compounds. All living structures are carbon-based. The Earth's crust has only 0.02% carbon in the form of minerals like carbonates, hydrogen carbonates, coal and petroleum, and the atmosphere has 0.03% of carbon dioxide. In spite of this small amount of carbon available in nature, the importance of carbon seems to be immense. Bonding in carbon, the covalent bond. Melting points and boiling points of some compounds of carbon. Compound. Melting point K. Boiling point K. Acetic acid, CH3COOH. 290. 391. Chloroform, CHCl3. 209. 334. Ethanol, CH3CH2OH. 156. 351. Methane, CH4. 90. 111. Most carbon compounds are poor conductors of electricity. From the data on the boiling and melting points of these compounds, we can conclude that the forces of attraction between these molecules are not very strong. Since these compounds are largely non-conductors of electricity, we can conclude that the bonding in these compounds does not give rise to any ions. The atomic number of carbon is 6. Carbon, it has 4 electrons in its outermost shell and needs to gain or lose 4 electrons to attain noble gas configuration. If it were to gain or lose electrons, 1. It could gain 4 electrons forming C4 anion. But it would be difficult for the nucleus with 6 protons to hold on to 10 electrons, that is, 4 extra electrons. 2. It could lose 4 electrons forming C4 plus cation. But it would require a large amount of energy to remove 4 electrons, leaving behind a carbon cation with 6 protons in its nucleus holding on to just 2 electrons. Carbon overcomes this problem by sharing its valence electrons with other atoms of carbon or with atoms of other elements. The shared electrons belong to the outer shells of both the atoms and led to both atoms attaining the noble gas configuration. The simplest molecule formed in this manner is that of hydrogen. The atomic number of hydrogen is 1. Hence hydrogen has 1 electron in its K shell and it requires 1 more electron to fill the K shell. So 2 hydrogen atoms share their electrons to form a molecule of hydrogen, H2. Hydrocarbons. Compounds which are made up of carbon and hydrogen, they are known as hydrocarbons. There are 2 types of hydrocarbons found, saturated hydrocarbons and unsaturated hydrocarbons. Saturated hydrocarbons consist of single bonds between the carbon atoms. For example, alkanes. Alkanes are saturated hydrocarbons represented by a formula, CnH2n plus 2. Unsaturated hydrocarbons are the one with double or triple bonds between the carbon atoms. For example, alkenes and alkena. Alkenes are represented as CnH2n whereas alkena are represented as CnH2n-2. Some saturated hydrocarbons and unsaturated hydrocarbons are represented as saturated hydrocarbons. CH4 methane, C2H6 ethane, C3H8 propane, C4H10 butane, C5H12 pentane, C6H14 hexane, C7H16 heptane, C8H18 octane, C9H20 nonane, C10H22 decane. Unsaturated hydrocarbons. Ethane C2H4, propene C3H6, 1-butene C4H8, 1-pentene C5H10, 1-hexene C6H12, 1-heptene C7H14, 1-octet C8H16. Allotropes of carbon. Allotropy, the phenomenon in which the element exists in 2 or more different physical states with similar chemical properties, are called allotropy. Carbon has 3 main allotropes. Diamond. In this carbon, an atom is bonded to 4 other atoms of carbon forming 3-dimensional structures. It is the hardest substance and an insulator. It is used for drilling rocks and cutting. It is also used for making jewelry. Graphite. In this, each carbon atom is bonded to 3 other carbon atoms. It is a good conductor of electricity and used as a lubricant. Buckminster fullerene. It is an allotrope of the carbon-containing cluster of 60 carbon atoms joined together to form spherical molecules. It is dark solid at room temperature. Versatile nature of carbon. The existence of such a large number of organic compounds is due to the following nature of carbon: catenation, tetravalent nature. Catenation, the self-linking property of an element, mainly carbon atom, through covalent bonds to form long straight, branched and rings of different sizes are called catenation. This property is due to the small size of the carbon atom, the great strength of the carbon-carbon bond. Carbon can also form stable multiple bonds, double or triple, with itself and with the atoms of other elements. Straight chain, propane, butane. Branched chain, 2-methylpropene. 2,2-dimethylpropane rings. Cyclohexane, cyclobutane. Tetravalent nature. Carbon has valency of 4. It is capable of bonding with 4 other atoms of carbon or some other heteroatoms with single covalent bond as well as double or triple bond. Hydrocarbons, compounds of carbon and hydrogen, are known as hydrocarbons. For example, methane CH4, ethane C2H6, ethene C2H4, ethine C2H2, etc. Saturated hydrocarbon alkanes, general formula is CnH2n plus 2. N equals number of carbon atoms. In this, the carbon atoms are connected by only a single bond. For example, methane CH4, ethane C2H6, etc. Unsaturated hydrocarbons. Alkenes, general formula is CnH2n, where N equals number of carbon atoms. In this, the 2 carbon atoms are connected by double bond. Alkene, general formula is CnH2n-2, where N equals number of carbon atoms. In this, the 2 carbon atoms are connected by triple bond. Electron dot structure of hydrocarbons. Methane, ethane. Isomerism, compounds having the same molecular formula but different structural formula and properties are known as isomers, and this phenomenon is known as isomerism. Structural isomerism, compounds having the same molecular formula but different structures are called structural isomers. Example, isomers of butane C4H10, N-butane 2-methylpropane isobutane. Isomers of pentane C5H12, N-pentane 2-methylbutane isopentane. Isomers of hexane C6H14, N-hexane 2-methylphentane isohexane. 3-methylphentane 2,2-dimethylbutane. Homologous series of organic compounds having the same functional group and chemical properties and successive members differ by a CH2 unit or 14 mass units are known as homologous series. Homologous series of alkanes, alkenes and alkene. Alkanes. Methane CH4. Ethane CH3 single bond CH3. Propene CH3 single bond CH2 single bond CH3. Alkenes. Ethane CH2 double bond CH2. Propene CH3 single bond CH double bond CH2. Alkene. Ethine CH triple bond CH. Propyne CH3 single bond C triple bond CH. Characteristic of homologous series, the successive members in homologous series differ by CH2 unit or 14 mass unit. Members of given homologous series have the same functional group. All the members of homologous series show similar chemical properties. Functional group, an atom or group of atoms present in a molecule which largely determines its chemical properties, are called functional group. Functional group suffix prefix 1. Identify the number of carbon atoms in the compound. 2. Functional group is indicated either by prefix or suffix. Alkenene, alkene yne, alcohol ol, aldehyde ketone on, carboxylic acid OIC acid, chlorine chloro. 3. If a suffix is added, then final A is removed from the name, e.g. methanol, methane A equals metham plus ol. Combustion. Carbon along with its compound is used as a fuel as it burns in presence of oxygen to release energy. Saturated hydrocarbons produce blue and non-sooty flame, whereas unsaturated hydrocarbons produce yellow sooty flame. CH4 plus 2O2 is equal to CO2 plus 2H2O. Oxidation. Alcohol can be oxidized to aldehydes, whereas aldehydes in turn can be oxidized to carboxylic acid. Oxidizing agents such as potassium permanganate can be used for oxidation. Alcohol is equal to aldehyde is equal to carboxylic acid. Addition reaction. Hydrogenation of vegetable oil is an example of addition reaction. Addition of hydrogen in presence of catalysts such as nickel or palladium. This converts oil into ghee. Ethylene plus bromine, brownish red, is equal to 1,2-dibromoethane. Colorless. Substitution reaction. When one atom in hydrocarbon is replaced by chlorine, bromine, etc., this is known as substitution reaction. CH4 plus Cl2 is equal to CH3Cl. Chloromethane. HCl. Important carbon compounds, ethanol and ethanoic acid. Ethanol is a volatile liquid with low melting point. It reacts with sodium to form sodium ethoxide. 2Na plus CH3CH2OH is equal to 2CH3CH2ONa plus sodium ethoxide plus H2. This reaction is used to test the presence of ethanol by the evolution of hydrogen gas. Dehydration of ethanol in presence of hot sulfuric acid forms alkene. CH3CH2OH. Hot concentrated H2SO4 is equal to CH2 double bond CH2 plus H2O. Ethanoic acid is a colorless liquid. When pure ethanoic acid freezes like ice, it is known as glacial acetic acid. It is formed at a temperature of about 16.6 degrees centigrade. Ethanoic acid, acetic acid, when reacts with ethanol, it forms an ester. Ester can be identified by its sweet smell. Ethanoic acid plus ethanol is equal to ethylethanoate ethyl acetate. Reaction of ester with strong base is used to form soap. This is known as saponification. Acetic acid also reacts with strong base to form sodium acetate and water. NaOH plus CH3, not COOH. Plus CH3, COONA. Plus H2O. Soaps and detergents. Sodium or potassium salt of carboxylic acid is known as soap. They work most effectively in soap water. Detergents are sulfonate or ammonium salt of long chain of carboxylic acid. They can work effectively on soft as well as hard water. Cleansing action of soaps and detergents. Cleansing action of soaps and detergents is due to ability to minimize the surface tension of water, to emulsify oil or grease and to hold them in a suspension of water. When soap dissolves in water, it forms soap anions and soap cations. The hydrophobic part of soaps and detergents are soluble in grease and hydrophilic part is soluble in water. Soap and micellar formation. When dirt and grease are mixed with soap water, soap molecules arrange them in tiny clusters known as micellar. The hydrophilic part sticks to the water and form outer surface of the micellar, and hydrophobic part binds to oil and grease.